This video contains the solutions to the vector fields practice problems. For this first problem, we're trying to match up the algebraic description of the vector field with the graphical representation of that same vector field. So let's try to pick the vector fields that look a little bit more simple and see if we can match those up first. So I'm talking about B and C here, where the x component is 0. So the fact that the x component is 0, what that tells us is that all of the vectors in this vector field point only in the y direction. They only point up or down. They never point to the left or to the right. So we can tell that of the 4 vector fields we have, the only ones that satisfy that are these 2 here at the bottom. So those are the only ones where the vectors solely point up or down, not to the left or to the right. So now let's think about what the y component being negative x would mean. That means that when x is positive, in other words in quadrants 1 and 4, my vectors point in the negative direction. When x is positive, these vectors are going to be pointing down. So in quadrants 1 and 4, all of the vectors point down. And we can see that that happens here in this vector field on the left. So that must match up with B. And again, just to verify, 0, comma y, that would mean that when y is positive, in other words in quadrants 1 and 2, all of the vectors only point up. And that we can see here as well. When y is positive, the vectors point in the positive y direction, and so that must match up with option C. Now let's figure out which the other ones match up with. For A, we have x comma y. That means when x is positive and y is positive, the x component is positive and the y component is positive, which means in quadrant 1, the vectors always point up and to the right. So here in quadrant 1, we see that all of the vectors are pointing up and to the right. That's not true of the vector field on the left here. And so this must be option A. And again, just to verify, we have minus y comma x. So in quadrant 1, what should we expect to see? In quadrant 1, y is positive, so that means the x component is negative, so these vectors should point to the left. In quadrant 1, x is positive, so that means the y component is positive, which means these vectors will point up. So in quadrant 1, we would expect all of the vectors to be pointing up and to the left, and we see that here in quadrant 1. And so this must be option D. Now we want to find the gradient field for a potential function. So a potential function is just the name for this function phi that we're talking about, and the vector field is simply the gradient of phi. Now remember that the gradient of phi is just the vector that has the x component of phi in the x component, and the y partial derivative of phi in the y component. So the x partial derivative is going to be 1/2 times x squared plus y squared to the minus 1/2, multiplied by the derivative of x squared plus y squared, which is 2x, because I'm taking the partial with respect to x. The partial with respect to y is going to be similar, 1/2 x squared plus y squared to the minus 1/2, multiplied by the derivative of x squared plus y squared, which is 2y. So if I wanted to simplify this, I would get x divided by the square root of x squared plus y squared, comma, y divided by the square root of x squared plus y squared. Now that we have that vector field, what we want to show is that that vector field, the gradient field, is normal to the equipotential curve, which is just a level curve of this phi function at the point 2, comma 1. So we've got our function phi of xy, which is the square root of x squared plus y squared, and we've got our vector field f, which, as we figured out in the previous problem, is x over x squared plus y squared, comma, y over x squared plus y squared. So how do we show that at the point 2, comma 1, these two things are perpendicular? Well, first let's figure out the value here. The vector field at the point 2, comma 1 is what we get when we plug 2, comma 1 in for x and y. That gives us 2 divided by the square root of 5 and 1 divided by the square root of 5. So how would we show that that vector is perpendicular to the curve phi of xy equals phi of 2, comma 1? Well, remember that we can figure out the slope of the tangent line to that curve at that point. By taking minus the x partial of phi divided by the y partial of phi. Now we already know the x and y partials of this function, so this is going to be minus x over x squared plus y squared over y over square root of x squared plus y squared. Simplifying that, we just get minus x over y. And at 2, comma 1, this slope is negative 2. Negative 2 over 1, which is negative 2. So that means that the tangent vector or a tangent vector that we could find, is 1, comma, negative 2. Remember that the slope gives the change in y over the change in x, so that means that if I make the change in x be 1 and the change in y be negative 2, then that will be a vector that's tangent to this curve. So all we have to show is that these two vectors, the tangent vector to the curve and the vector in the vector field, are perpendicular to each other. And the way that we check for perpendicularity is by taking a dot product. So this is going to be 1, comma, negative 2, dot 2 over radical 5, comma, 1 over radical 5. That's going to give us 2 over radical 5 minus 2 over radical 5, and sure enough, that turns out to be 0. We're going to do the same kind of problem again. First, we're going to find the gradient field. So my vector field f is going to be the gradient of phi, which is the x partial of phi, comma, the y partial of phi. This time the x partial turns out to be 4xy minus 2y squared, and the y partial will be 2x squared minus 4xy. Now that we have that vector field, again what we want to show is that at the point 2, comma 1, the vector field is perpendicular to the level curve. So let's find the vector in our vector field at the point 2, comma 1. Capital F of 2, comma 1 is what we get when we plug in 2 for x and 1 for y. And in this case, that vector is 6, comma 0. Now we need to find a vector that is tangent to the level curve phi of xy equals phi of 2, comma 1. And again, we're going to find the slope of the tangent line to the curve phi of xy equals phi of 2, comma 1 at the point 2, comma 1. The slope of the tangent line is minus the x partial of phi divided by the y partial of phi. And we know what that is. The x partial is 4xy minus 2y squared, and then the y partial is 2x squared minus 4xy. When we plug in 2, comma 1, however, what we get is minus 6 divided by 0, and that's undefined. So what is that telling us about this curve at that point, 2, comma 1? Well, if the slope of the tangent line is undefined, that means the tangent line is a vertical line. So a vector that points in that tangent direction would be a vector that points only vertically. And so one vector that we could use would be the vector j, 0, comma 1. Now, why are these two vectors perpendicular? We take a dot product. It should be pretty clear why they're perpendicular, but let's just verify it. 0, comma 1 dotted with 6, comma 0 is 0 times 6 plus 1 times 0, and that is, of course, 0.